welcome to a video about light sources. Light sources are objects that emit light from the visible section of the electromagnetic spectrum. So the learning intentions for this video are that monochromatic light is light composed of a single frequency. Most light sources emit waves that radiate in all directions away from the source. Coherent wave sources are wave sources that maintain a constant phase relationship with each other. In Stage 2 physics, you need to be able to describe what is meant by two wave sources being in phase or out of phase, and you also need to be able to explain why light from an incandescent source is neither coherent nor monochromatic. So, our types of light: monochromatic is visible light composed of a single frequency. It can be emitted in one or more directions, and examples of this are lasers, and they emit monochromatic light in one direction. You can also get LEDs. These emit one colour of light, so they're monochromatic, but the waves are not coherent, and we'll touch on what that means in just a moment. Monochromatic light in reality is unattainable, and that's for some uncertainty reasons. So I think it's called Heisenberg's uncertainty principle. For whatever reason, it's impossible to get like exactly one frequency of light, and the reason for that is to do with how the light's produced. It's produced from the energy levels, from the changing energy levels of electrons in atoms. It's not possible to control that super specifically. You can get a roundabout kind of range of frequencies that an atom will emit, but you can't control it to one frequency. So there's in real life it's impossible to get monochromatic light, but we can get as close as possible. Now, I mentioned coherent waves just before when we were talking about lasers. Coherent waves are waves that are in phase. So what I mean by in phase is that their positions are matching in the wave cycle. And in order to achieve this, they must have the same frequency. So if we have a look at the laser picture here, at this point, the bottom wave is at its peak, the middle wave is at its peak, and the top wave is at a peak. At this point, the top wave is at a trough, the middle wave is at a trough, and the bottom wave is at a trough. So each wave is at the same position in its wave cycle. So perhaps if you want to write a definition down, you can pause the video and write. So phase itself means position within a wave cycle. In phase means that the wave cycle positions of any two waves or multiple waves overlap. And out of phase means that there is a phase difference between identical positions on multiple or two given waves. And just to reiterate, in order to be in phase and therefore coherent, waves must have the same frequency, because if they don't have the same frequency, how can their completely different wave cycles match up? And then lastly, incandescent light is visible light composed of different frequencies, and it's emitted in all different directions. And examples of this are sunlight and filament globes, so globes that burn the little filament. This is made up of various different frequencies. So in sunlight you've got all of the visible light frequencies that combine together, not in a superposition way, but in the light itself. It's composed of all of these different frequencies that are getting shot out from the sun together. In a light globe, there's a range of different frequencies as well. It's not quite all of the frequencies of the visible light spectrum, but it covers like enough sections to appear like sunlight in a way. So when you combine all of those frequencies of the visible spectrum, then you get white light. And a filament globe is like a good approximation for that. So it is combining enough sections of the light spectrum to appear white. Another learning intention for this video is that when two or more electromagnetic waves overlap, the resultant electric and magnetic fields at a point can be determined using the principle of superposition. When the waves at a point are in phase, constructive interference occurs. When the waves at a point are out of phase, destructive interference occurs. And in stage 2 physics, you need to be able to use the principle of superposition to describe and represent constructive and destructive interference. So we'll look at superposition now. Superposition applies to all types of waves. We'll look at it specifically with respect to electromagnetic waves. So when multiple electromagnetic waves with the same frequency overlap, their fields add vectorially. So waves that are in phase, so the same point of the wave matches up with the same point on another wave. These waves will interfere constructively, so it means that the displacement of both of these waves will stack, and the electric field as well as the magnetic field will both increase in magnitude. If waves are out of phase, their displacements will add together, but the overall magnitude of the displacements will therefore decrease. So this is destructive interference. So, for example, one crest of one wave might be adding with the trough of another wave. And then if it's the peak of the crest adding with the peak or the maximum part of the trough, then they'll completely cancel out, and there'll be like zero displacement there for the wave. So if they're out of phase by half a wavelength, this complete cancellation occurs. And just a reminder that the waves must be overlapping with equal frequencies. You can get destructive interference that occurs that isn't a complete cancellation, but if the waves have equal frequencies and equal magnitudes, then they'll cancel out completely if they're if they're half a wavelength out of phase. If waves aren't a half wavelength out of phase, you might get a little bit of constructive interference as well as a little bit of destructive interference, but it won't completely cancel to nil. In terms of visible light, the tangible impact of constructive interference is that light intensity increases. The tangible impact of destructive interference is that light intensity decreases. The last learning intention for this video is for monochromatic sources. In phase, the waves at a point some distance away are in a vacuum, constructively interfere when the path difference from sources to the point is an integer multiplied by the wavelength, and destructively interfere when the path difference from the sources to the point is an integer plus a half multiplied by the wavelength. In stage 2 physics, you need to be able to use the principle of superposition to determine points of maximum or minimum amplitude resulting from the interference of light from two wave sources of the same frequency. You also need to be able to use constructive and destructive interference to explain the maximum and minimum amplitudes. So we'll take a look at monochromatic interference. So remember, monochromatic light is visible light composed of a single frequency. Remember, it's like an ideal physics land kind of thing. In real life, you can get close to light of a single frequency, but in physics land, we'll say that you can have light of a single frequency. So monochromatic interference occurs if the waves leaving two monochromatic wave sources arrive at a point in phase. So the position of their electric field and magnetic field displacement. So for each displacement, the position of those waves is the exact same as the position of the waves of the wave that they're meeting, or the waves that are meeting. And this occurs if the path difference, so the length from each source to a point, is an integer number of wavelengths. On the next slide, we're going to look at a diagram. So hopefully, if it's sounding a little bit abstract now, it'll make more sense on the next slide. Waves leaving two monochromatic wave sources will interfere destructively at a point if they arrive half a cycle out of phase. And this occurs if the path difference is an integer plus a half number of wavelengths. So m plus half multiplied by lambda, where m is 0 onwards, but just integers. So if you're looking at whatever this term here is going to be, so the thing multiplying lambda, if you're starting at m equals 0, you'll just get half multiplied by lambda. If m equals 1, you'll get 1.5 multiplied by lambda, and so on. So half, 1.5, 2.5, 3.5, and so forth. Whereas up here, it's just the integer number multiplied by lambda, and the integers start from 1. So this is what we're talking about when we're talking about path difference. So we've got a monochromatic light source here, we've got a monochromatic light source here, and both of these monochromatic light sources emit light of the same frequency. So we've got light travelling along the blue line, or the blue path, and the light has travelled 6 wavelengths in order to get to this point here. The light from source 2, so the light travelling along the red path, has travelled 8 wavelengths in order to get to the same point. So because the difference between the two paths is 2 wavelengths, so 8 wavelengths minus 6 wavelengths is equal to 2 wavelengths. Because this number here is an integer, so it's 2 is a whole number, then the waves are going to interfere constructively, because this number here, m, is an integer. So the path difference between the two sources of light, or sources of monochromatic light, to the point that they're meeting at is 2 wavelengths. So the same point of the red wave is meeting with the same point of the blue wave, and they'll constructively interfere. If we look across to the right hand side, we've got monochromatic light source 1, monochromatic light source 2, and the point that they meet at. It takes the light from source 1 3.5 wavelengths to get to this point, and it takes the source 2, so the light travelling along the red path, it takes 4 wavelengths. So the difference between 4 wavelengths and 3.5 wavelengths is half a wavelength. So if we go back to the previous slide, because the path difference is an integer plus a half number of wavelengths, then the waves will interfere destructively because they're half a cycle out of phase. Maybe where there's a peak in the first wave, there's a trough in the second wave, and they'll combine to cancel each other out, so there'll be destructive interference there. The bottom diagram here shows the interference from two monochromatic wave sources. So these are the sources here in the middle. You can kind of think of it maybe as like two ripples. And the minimum of each wave is represented with an orange line, the maximum with a blue line. So you can see where a blue line meets a blue line, you'll get constructive interference, and where a orange line meets an orange line, you'll get constructive interference as well. For the blue lines, the interference will be in the positive direction, so the two peaks will combine and form a greater peak, and then with the orange lines, the two minimums will combine to form like an even bigger minimum. That doesn't sound like it makes sense, but the minimum will be a bigger number, or like the magnitude of the minimum will be a bigger number. And where orange and blue lines meet, you'll get destructive interference, so the maximum will be cancelling out with the minimum of the other wave.